Good afternoon, everybody, and welcome to this webinar for the Italian site demo of 5G. It's the third demo in a row, the fourth actually, if we encompass also the one that we made at the beginning related to the Spanish demo. Then we had the French one and the Greek one in July, and now it's time for showing you the activity in the Italian side. In this workshop, you will see the use cases that are almost all those that are internally conceived in 5G. Some general remarks for this webinar. So first of all, I'd like to inform you that this webinar is being recorded. Secondly, I kindly ask you to ask a question just at the end. There will be a question and answer session at the end of the presentations. Or otherwise, you can use, of course, the chat anticipating your questions. Final remark, I'd like to inform you as well that this webinar is actually made totally online. We don't have, as we hoped to have some live activity in our so-called Innovation Mile in Turin, due to the fact that in this period, the area of Turin is under lockdown for coronavirus. And so there is no possibility to send people to have some live experiment in our premises in the area that we are covering with 5G, commercial 5G from Telecom Italia. So anyway, this webinar will be complete in the sense that we have some pre-recorded material, and we have some, and we have anyway the possibility of showing you live the management of data and most of the contents of the use case. So welcome again. That's all from my initial greeting and presentation. I'd like to now leave the floor to Silvia Canale from RS2T that will lead the presentation and will guide you through the different parts of it. So welcome, Silvia.
Thank you, Mauro. Thank you as a project coordinator for this introduction to this webinar. I will present an overview of the webinar in order to anticipate and to give an outlook of the three main presentations that will follow this overview. The three presentations focused on a single use case, namely smart transport, presented by RS2T, smart city, presented by CNIT, and smart tourism, presented by CNIT. So the three independent presentations will follow with the execution and the main results of the use case execution. And at the end, we will have time for the Q&A session. So let me just give you a general presentation of the use cases. Why? Because the three use cases we selected for the Italian site has some common objectives and motivation behind the selection and execution of these specific use cases. The methodological framework is similar in some sense, even if the technologies are different. So we would like to make comparison among them. And of course, we would like to present the vertical key performance indicator playing a fundamental role for the verticals interested in these specific use cases. The testbed is common, is the Italian site of the 5G facility. And of course, the flow we adopted, execution is common for use cases. And after, we will give the presentations with specific details, use case by use case. In 5G, there are 6 internal verticals, and 6 of them are focused on mobility in urban area. The three of them are smart transport, in a use case called the urban mobility 5G data flow analysis, whose the goal is the identification of anonymous mobility patterns in urban area by automatic recognition of the user transport mean for traffic management and peak prevention purposes in local public transportation as well as railway station management. Smart City, namely the use case Smart Turin Wi-Fi scanner, has the goal of analyzing anonymous mobility flows in urban areas, where, of course, safety and security must be monitored and the large crowd gathering should be detected, possibly real time. Smart Tourism finally developed an augmented reality-based application exploiting the support of 5G new generation networks for live interaction and multimedia content access requiring massive data processing and communication. What are the motivations of these three use cases? In smart transport, we would like to show that thanks to the 5G mobile communication, it's possible analyzing real-time massive raw data through large-scale data analytics, providing added value information for decision-making traffic congestion management in urban areas. In smart city, the motivation derives from the pervasiveness of mobile devices, allowing to define specific electromagnetic signature for each person. So in this case, the Wi-Fi scanners are spread out in the area and are distributed across this area, allowing identifying people mobility flows in an anonymous way. In smart tourism, the main motivation is the enhancement of the fruition of architectural heritage, that is very rich actually in the city of Turin, and to support the holistic and inclusive intelligent touristic experience. So the three motivations are, of course, very different, but the data and the algorithms approach is quite similar. In smart transport, for example, data are collected from sensors built in user mobile device, so the current mobile device everyone has. So no additional equipment is required. The data analysis is performed via multi-access edge computing server in a distributed and parallelized way and close to the data source. In this case, the service returns each user with a real-time estimation of the transportation modalities and publish the mobility patterns, the aggregated and anonymous mobility patterns, on the multi-tenant platform owned by TEAM, namely the one machine-to-machine icon. In smart tourism, data are collected from Wi-Fi scanners spread out in the so-called innovation mile, we will see later on, and connected to the mobile network. So there is no actual involvement of the end user in that. In the data analysis is performed via multi-access edge computing server in a distributed way and very close to the data sources with no access to the core network. In this case, the service returns the number of devices each scanner is on and allow to show the mobility flow on a map. In smart tourism, massive data needed by the AR application are fed to mobile user from the multi-access edge computing server and very close to the data source. In this case, the service is extremely responsive, of course, by exploiting the powerness of 5G networks, and the user experience is, of course, enhanced. Which are the main vertical KPIs we are observing in our use case execution? In smart transport, mainly we are interested in measuring response time and memory usage, of course. And in this case, for tracking the data and to recognize the modalities, response time and memory usage are in some sense connected to the vertical network KPI, except the accuracy, that of course is the main indicator for the software data processing that we made about the data. In smart city, on the other hand, the CPU usage and the memory usage is as much important as the bandwidth. And of course, the two families of vertical KPIs are strictly connected to the typical network KPIs, the availability, the latency, and the device density, because we are talking about massive data collected in a distributed way in the area. For smart tourism, the memory usage, when we talk about massive data analysis, is crucial. And of course, the network latency allows the enhancement of the touristic experience. So the two KPIs play a very important role. Let me just introduce the testbed. The testbed common to the three use cases. On the right-hand side of this slide, you can see a portion of the so-called innovation mile between the second main railway station in Turin, namely Torino Porta Susa railway station, and the campus, the Turin campus, namely Politecnico di Torino, in the south part. In behind, you can see enlarged in the left-hand side of the slide, you can see the area that will host our use cases, so this portion of the innovation miles, with the distribution of the 9 Wi-Fi scanners used in the smart city use case, and the localization of the 5G base station in the south, very close to Politecnico, in the premises actually of the Politecnico di Torino. The framework we adopted, of course, is the one holds for any internal and external use cases in 5G Eve. In this experiment flow, there are 4 families of activities. The first one is the experiment design activities. In this case, the service and the experiment is analyzed, and all the software packages necessary to support the development of this use case are onboarded. There is a specific experiment design activity focused on the definition of both the service and the experiment, of course. In the experiment preparation activities, the experiment is customized and scheduled. And of course, from the site manager point of view, the experiment environment is prepared to run the execution. The execution comes in the third step, where the experiment is dynamically instantiated and the test is executed, the single test case is executed. At the end of the 3 steps, of course, we have the experiment result analysis activities, where all the KPI, both network and vertical KPIs, are analyzed after they are recorded during the experiment execution. And now we can start from the first use case we have the pleasure to present today in this webinar. The first use case among the Italian site demos is focused on vertical smart transport and is the use case dedicated to the utility 5G data analysis, flow analysis. The presentation is given by Aristuti, that in this use case played the role of vertical and use case developer, me, Silvia Canale, and my colleagues Alberto Rainieri and Vincenzo Suraci. To develop this use case, there are 3 main services powered by 5G Eve to mainly enhance multimodality between the railway station, the railway network, and the collective transportation services in the urban areas, already present in the urban areas. We started to develop a 5G tracking service to collect and transmit raw data from sensors. These sensors are located, they are built in the end user's mobile device, so there is no additional equipment, no Wi-Fi scanner, no other IO things sensor distributed on the way. There is only the mobile phone owned by the end user, and via the dedicated 5G multi-access edge computer, these data are collected and are sent to the recognition service, the second service we developed to support this use case. This recognition service analyzes the collected data and automatically identifies the user mobility patterns and actual status of the user, if he's walking or running around, as well as the transportation modalities in the case he's driving his car or he's just got a metro, a tram, a bus, other public transportation system. At the end, the urban mobility service we developed collects both raw data coming from the sensor and the identified status or the modality, transmit the enriched information, so the actual patterns, as well as the GPS coordination of these patterns, to the multi-tenant one machine-to-machine platform owned by team. The purpose of the use case realized by these three services are a number of purposes, but specifically we were focused on the identification of different transportation modality demands. That is very important in urban area because it's a very difficult task. Performing a spatial planning that is crucial for the spatial urban mobility planner as an institution, as an agency in the administration of a smart city like Turin, and of course to enable efficient trip planning and real-time control according to the mobility patterns and their actual flows. So the typical use case we are interested to develop is something very similar to the one you can see in these slides. We imagine that the end user, Paul, arrives in Torino Porta Susa, so at the railway station, from Milan by a high-speed train, Frecciarossa. As his device is connected to the 5G antenna in the urban area of Turin, the tracking service starts collecting data series from his mobile devices. So he's walking, and the recognition service recognizes Paul as a walker. So the urban mobility service starts a mobility profile, associating a specific mobility profile to Paul, starting from walker. When Paul rents a car to get to the campus, the tracking service continuously collects data from his mobile device, and the recognition service changes the transportation modality from walking to car, identifying Paul as a driver. So in this case, the urban mobility service continuously enriches the mobility profile associated to Paul, and when he stops by the campus, the recognition service recognizes again him as a walker, and the mobile service finalized the mobility pattern associated to Paul, and of course update the mobility patterns in the area between the railway station and the campus. So this, of course, is realized by a 5G connection to the base station and the recognition service running through the multi-access edge computing. So we realize, and now next slide we can see how it works, a tracking mobile application, an Android application, mobile application, that will be used by our end user, that you will see in a minute, for collecting and sending data to the backend system to communicate the estimated transportation mode. So the Android application is used to send data, but also to return back the estimated transportation mode, so that the user can identify is the recognition is correct or not. And the recognition service is a back-end software system analyzing and estimating real-time the user status, still working or running, as well as the transportation mode through machine learning-based recognition models. So behind the recognition service, there is a huge campaign for data collection and massive data mining to identify these recognition models the service relate to. And finally, the Info Mobility Service is a software application with the aim of providing aggregated information in terms of mobility flows and patterns. They are specifically of interest of the actors, mainly the municipality of Turin, via the one machine-to-machine, the platform, collecting all the data and enrich the information for the different purposes we have seen before. In the right-hand side, you can see an anticipation of the Android application, and now we can see the execution of the experiment. Let me just give you an overview before going to the detail of the environment, of the people helping us in realizing this use case. The experiment shows, so in brief, you will see the real-time mobility patterns of each user, so trajectory and the status of the transportation adopted by the users. So there will be two people in the execution of the experiment. The two people will use our 5G tracking mobile application to start the data registration session to indicate their status. In this case, we only limited to still walking and running with no mechanical transportation made options because of COVID-19 mobility restriction in the city of Turin, and to get back real-time status estimation. So we will see how many times the recognition service will return the correct label between among still walking and running. So the area is the test bed. The area that you can see depicted in the picture on the right-hand side of the slide is exactly the portion of the innovation mile chosen for the test bed for the 3 use cases, and the 2 icons indicate that one person will walk and the other one will run over the street. So 2 people, 2 devices, and now let's see how the environment is presented by Mauro Agus, that is the site manager of the Italian site.
Good afternoon, everybody. Now I don't see my video, so for me it's a bit difficult to. Okay, I see my video now. I just show you the environment. This is the environment and the guys that will help us. Okay, we have 2 devices, 5G devices that are 10, and on those devices we have a special SIM card that is able to connect to join the IPN in field that we have for the project. So we can reach the OpenStack platform by the private network of the Italian site of 5G. On the 2 devices, we already upload the 5G. If wait, okay, the focus works. We already upload the 5G the RS2T application. On this application, we can create a session, and we will start the log. Those 2 guys will walk, run, will move in the area, and the application will recognize the transport mode. Maybe Silvia can be more clear after in the presentation. So now we start the log, and we choose the first transport mode that is necessary just for the KPI evaluation. So now we declare to be still, and the demo is started. Okay. So now on both devices we do the same. Also, the transportation mode declared is still, and after 10 minutes, after the presentation that Silvia will show, we will see what happens in the device.
Okay. So while the use case is executed, I would like to give you a presentation of the architecture behind the use case. I would like to leave the floor to Vincenzo Suraci, that is the senior architect at RS2T. Vincenzo, can you hear me?
Yeah, very well. I hope you can hear me as well.
Yes, we do. Please go ahead.
So, as Silvia already introduced, this architecture has the objective to accomplish to three use cases: the tracking service, the recognition service, and the urban mobility service. All the for each of these service, we dedicated part of the depicted architecture. First of all, I would like to explain from an higher point of view the different components that you can see in this architecture. In the left side, we have the mobile device, the one showed by Mauro in the previous video. In fact, we need to collect data from the field, and we developed the Android app that connects to the REST part of the architecture. So we need, in the left side, an Android app to communicate with our facility. In the middle, we have the Italian site facility where all the servers, the virtual servers, are hosted. It is an OpenStack environment, and we have different machines that communicate each other. And in the top part of this architecture, we have two virtual machines, the number 1 and the number 2, that are in charge of providing the tracking service. The tracking service deals with the gathering of the information from the device sensors, and like the GPS, the gyroscope, and so on. And so we need something to collect all this data, and it is the backend tracker, the BE tracker virtual machine number 1. And this machine collects the data, analyzes the provided info. Let me say that we provide some data quality management, so that once the data are ready to be collected and analyzed, they are forwarded to the virtual machine number 2, that is a visualizer, so that we can have a glance on the received data. And we will show you in the next the typology of graph information, visual information that we can gather thanks to the virtual machine number 2. Since we handle a huge amount of data, we wanted to monitor the performances of this data visualization. And that's why we monitor the KPI needed for the memory usage and response time provided by the visualizer to the end user. And we keep track of this KPI and send them to the Kafka bus, that is a server, the virtual machine number 3, dedicated to collect all the KPI of the running experiments. In the right part of the slide, we have all the experimentation desktops that can connect to the visualization system of our specific service, as well as of other services, to monitor, to visualize the data. And in particular, in the top right side, we can have a look to the tracker, the service tracker dashboard, connecting to the OpenStack by means, obviously, of a VPN, a dedicated VPN channel, so that we can visualize the tracked data by means of a normal web browser. Indeed, in the virtual machine number 2, we host a Kibana server that helps to show graphs and very fancy data visualization. So this is the tracking service, and the main role in the tracking service is played by the virtual machine number 1. It not only collects the data, but it also develops the model applying for specifically programmed machine learning algorithms in order to best match the data that we collected by the mobility users to match the mobility mode that these users, these experimenters, helped us to recognize. So as soon as we did the very first experiment, the people that were running or going by car or by biking and so on, they provided the information, the real mobility mode they were performing. And thanks to that, we collected data and trained models to identify the specific mobility transport also from unknown data or from new data coming from other devices connected to our tracking service. And these models is used by the last virtual machine, the virtual machine number 4, that is in charge of applying for the recognition service. In this case, the mobile phone, the application in the mobile phone it sends information second by second to the backend recognition server. It applies the recognition model and identify the best matching transportation mobility in comparison with the provided sensor data. So using the GPS, the gyroscope, the accelerometers, we are able, both in presence of the GPS, so the precise position of the person, as well as from the environmental, the ambient sensors that somehow define the status of the mobility situation of the person, we're able to associate a probability that that person is moving in a specific way. For example, walking or just standing, or is biking or running using a car or other public transportation system like metro, tram, and so on. And the recognition data are collected and visualized by means of a Kibana visualization system. And this Kibana visualization system can be accessed by the experiment responsible using a simple web browser. And finally, at the end, the collected aggregated data are also sent to the urban mobility platform that is in charge of a team partner that is called One Machine to Machine Icon Framework, and we provide this aggregated data as open data inside the Icon platform. So whoever has the access to the Icon platform can reuse the mobility, the recognized mobility transportation mode to build upon this data also third-party services, mobility services. So Silvia, that's all from my side. I give you back the room.
Thank you, Vincenzo. Thank you for explaining us the architecture. Let me just spend just a couple of minutes, but of course this is the most important part, the deployment of the services via the 5G Eve portal. So in the experiment design and after that the experiment preparation phase, we onboarded, of course, the VNF necessary to support the development of the use case. But by the portal, we were able to onboard the specific blueprints that are the templates that we have to fill in with the actual information useful for the preparation, the instantiation, and the execution of the experiment. So we onboarded, first of all, the vertical service blueprint describing the links among the different services, the different virtual machine providing the VNF, the virtualized network function. And in the blueprint, we provided all the actual parameters to make these VNFs working together and of course to be dynamically instantiated from scratch. After the vertical service blueprint, we defined itself then the experiment blueprint with all parameters. So we gave general information, as well as we selected the vertical service blueprint, the context blueprint describing specific parameters for the context useful for single test cases. Of course, the network service descriptors and the KPIs we want to monitor during the experiment execution. So after the onboarding process, we were able to instantiate the experiment, to schedule the experiment, of course, to be approved the experiment execution by the site manager for the configuration of the environment needed to support the execution of the experiment, and finally to execute the experiment that was exactly what you were seeing in the video when the two people helped us to collect data by walking and by running, and to see how the recognition service performed in evaluating real time the current status of the two users. And of course, how to measure this accuracy by means of a visualization dashboard that we realized, the dashboard that Vincenzo was mentioning before. And now I would like to invite our colleague Alberto to explain us and to show us something more about this dashboard to assess the performance of the tracking and the recognition services. Alberto, are you there?
Yes, of course, Silvia. Can you hear me?
Yes, I can. Let me stop my video sharing so you can show us the dashboard to compare.
Of course. Thank you very much. Give me just 1 second.
Sure.
Okay. So, show the content. Okay, all right. So, can you see the what I'm sharing right now?
Yes, we can. We can see the map of Turin, city of Turin.
Of course. So, all right. So, thank you, Silvia. So, yes. Okay. So, as my colleagues already explained, we prepared the experiment, and we held the experiment the 13th of October. And in this period of time, as you can see here, from 2:30 p.m. to 3:15 p.m., then here we can see that we have collected some data thanks to the geopoints heat map. And here we can see that we are in Turin. So this is the location where we collected our data. So if we take a closer look to the map, this is the specific location where we collected the data. So what I want to show you in this 5-10 minutes is not just the vertical KPIs, but I just also want to show you how our services work, something interesting that you can see. So, for example, here we are in the Kibana monitoring tool of the tracking service. So, thanks to this service, we are able to collect data. And thanks to this data, then we analyze them. And thanks to them, we can develop a machine learning algorithm that is then able to estimate the transportation mode. So, for example, in this experiment that we held the 14th of October, we performed 3 different transportation modes, like walking, still, and running. So, like we almost recorded nearly 1,000 of records. And this, just to show you something else, then each of these records have a bunch of features, like average GPS speed, linear accelerometer, magnetometer, magnitude. So we have a bunch of features, and thanks to them, we can develop a machine learning algorithm. And we believe that in the future, if we can collect more and more data, then we can even make our machine learning algorithm much more powerful. So now let's get to the part where I will show you some vertical KPIs. This is still, again, the Kibana monitoring tool of the tracking service. But as you can see here, we have max response time, memory usage. So we can collect these KPIs, vertical KPIs, and we can forward this data to our service, and then can then forward this data, these KPIs, to the 5G EVE platform. So this is also works for the recognition server. So now, if I go to the Kibana monitoring of the recognition service, so I recall you, this thanks to this service, so we are able to recognize the transportation mode, and the user can see from the app in real time what is the transportation mode estimated by the machine learning algorithm. So again, let's see what we have collected during the 13th of October in this Kibana monitoring tool of the recognition service. So again, here you can see two devices ID. In fact, during this experiment, two different users performed the still transportation modality, walking and running. And we collected the data thanks to the tracking service. And thanks to the recognition service, then we are able to see if the machine learning algorithm worked well. But I will also show you that here we consider in our experiment just still walking, running, but we have a wider range of transportation modalities like a bike, tram, car, bus, metro, train, motor. So the potentiality of our algorithm is very high. And so now it's time to show you the vertical KPIs. So for example, for the vertical KPIs, we have the recognition accuracy and the recognition network time. So again, the transportation modes that were declared were walking, still, and running. And for the walking part, we were able to estimate all of them. So 100% of accuracy was correct. And then again, for the still modality, most of them were correctly estimated. So like 38 out of 47. So it is a very good number. And then again, the running part, probably it didn't perform very well, just probably 4 out of 25. But as I said before, thanks to this tracking service, we can collect more data, and the machine learning can be developed thanks to this. And we believe that in the future, by collecting more data, then we will have better results. So we definitely have we have room for improvements. So again, in this experiment, the average accuracy was around 75%. And finally, I'll show you the last KPI, which is the recognition network time, which is the time elapsed in milliseconds between an inquiry to the 5G EVE recognition server and to the response to that inquiry, without considering the time spent for processing the request. So we can see that most of the time, the network time was under 150 milliseconds, and the average was about 148. So this is all from my side, Silvia. So I can get back to you.
Thank you, Alberto. Thank you so much. So Alberto shows us what was collected as KPI during the execution of the experiment. And now let's come back to the experiment execution. So the two people came back to the starting point of their walk or short run. And now, Mauro, we will show us how the application works from the user perspective. So providing us a look and feel of the modality estimated and real-time returned to the end user.
Now we go to the prediction, and if I see very still, you can see that the estimation is correct. After time, in the lower part of the screen
Mauro,
here.
can you read us what is written, because the quality of the image is quite bad?
Yes, yes. The top of the screen, you see that I declare still, and for some reason the car is detected, but in a couple seconds, because I have to refresh the screen. In the lower part of the screen, you can see the accuracy. Now accuracy is very low, as you see, because for some reason the phone detects that I'm in the car.
Try to move it.
Okay, now the still just because it was on the chair. Okay, now you see that the still is detected, declared and estimated. The maximum probability is still, and in the KPI part, now percentage of accuracy is going to increase because the transport mode is correct. So the maximum probability is still, so the accuracy is going to increase. I can try, it's quite difficult, but I can try to walk. Just let me try here to change transport mode to walk. Then open the prediction page and I start to walk. Now, I don't think it's very clear for you, but the detection not yet correct, because the KPI needs sometimes. Now the estimated is working. The couple seconds, so the probability is working. The KPI show the maximum accuracy because the estimation is correct.
Okay, in this video, Mauro showed us as the user can indicate, can declare a status or a modality, and how the estimation runs on the user application. So the estimated status or modality is on top of, and above you can see the probabilities, because the machine learning based recognition models provides additional information about the second and third possibility probabilities. So in this case, this application allows to have a clear idea what is going on from the tracking and from the recognition point of view. And of course, this application was developed only for testing purposes, so not for commercial use, of course, but is able to collect all vertical KPIs of interest for the use case. So now, before the conclusion, I would like to finish this presentation about the smart transport use case. We are on time, and I would like to give the floor to the other two use cases, the smart city and the smart tourism one. So I'm going to stop my video sharing, and I give the floor to Paolo. Paolo, can you hear me?
Yes, yes.
Okay, so
So let me share my screen. Can you see my slides?
Yes, we can.
Okay. So good afternoon to everybody. So in this use case, as already anticipated by the nice introduction of Silva, we take a complementary approach to investigate the mobility with respect to the previous use case. The previous use case was taking a kind of microscopic approach because it was focusing on the mobility of a single person. Instead, here we take a macroscopic approach that is investigating the mobility of aggregation of people. So what we have the area, an area that is covered by some Wi-Fi scanner, and what we are able to do. Actually, we are able to monitor in real time the number of people under the coverage of each Wi-Fi scanner, like in this case. And the second thing, we are able also to identify the mobility pattern. So basically find the trajectory followed by the people. And in addition to this, we are able to provide the access to the historical data that could be also useful for offline processing. Actually, in our use case, we are not really counting the number of people. We are counting the number of Wi-Fi devices like a smartphone that are, of course, strictly correlated with the number of people in a given area. This is the test bed. We have, if you see in the innovation mile we mentioned before, we have here Politecnico di Torino. Here we have Torino Porta Susa train station. This is one very large road that is typically very busy, and it is also some. It is I mean, this road is used also by commuters to go from our campus area to the train station. And then we have these scanners that are actually Libelium scanner that have been installed at the top of some traffic lights. This is the architecture. So we have the smartphone whose presence is detected by the Wi-Fi scanner. The Wi-Fi scanner sends the information to one M2M platform. And now we have our application running at the edge cloud. This application has been developed in two virtual machines. One is the mobility tracker that is responsible to retrieve the data from the one M2M platform and process this data. And then we have one virtual machine that it is responsible to create all the dashboard that are used by the user who is here. So later during the live demo, I will be connected with my laptop actually to this visualization virtual machine. How does the Wi-Fi scanning works? I don't know if you are aware, but your smartphone, if it is not associated to an access point, it is sending periodically some messages called probe request to check if there is some well-known access point nearby. So our idea is to exploit the source MAC address of these messages as a kind of fingerprint of your smartphone. So in order to evaluate the number of people that are in the area, we should just count the number of distinct MAC addresses. This process seems quite simple, but in practice very hard because sometimes the MAC addresses are randomized to preserve privacy. That means that your smartphone every 10 seconds, minutes, really depends on the implementation on the device, on the use of the device, changes on purpose the MAC address. And this, of course, creates a bias in the estimation because if you count just the distinct MAC address, you have basically an upper bound on the number of the device inside the area. So actually what we did was, since the MAC address are actually anonymized from the moment in which they are received by the Wi-Fi scanner. So basically we have, this was the original MAC address that we don't see, only the Wi-Fi scanner sees. This is collected, this is stored and stored in the one M2M platform as this long string is a SHA-224 hash function. And from this anonymized MAC address is impossible to understand if it has been randomized. So what we did was to consider a collection of non-randomized MAC address that we were able to get from in our campus. So we were able to collect through the Wi-Fi available inside the campus the MAC address not randomized, so it is the real MAC address of 32,000 Politecnico students and around 3,000 Politecnico employees, most of them faculty. Or another approach is to consider the case in which the same anonymized MAC address appears in distant time. This means that you can expect that this means that the MAC address has not been randomized, because typically the randomization occurs with some short time scale. These are the dashboard by which we are able to analyze the results. I will show basically later in the live demo two dashboards. This is the dashboard for to show the device density, so the number of devices under each Wi-Fi scanner. And this is the other dashboard that it is used to detect the flow mobility pattern. We have also integrated our use case in the 5G EVE portal. I'm not going into the details because this is replicates exactly what Silvia described for his use case. So we are able to, I mean, we have this screenshot of the onboarding process for the vertical service blueprint. This is the wizard for the creation of the experimented blueprint. We have also the integration with the metrics and KPI visualization. So now what I'm going to do, I will do briefly a live demo in which I will start showing the dashboard for the device density. Then I will move to the dashboard for the user mobility pattern. And then I will leave the floor to Matteo Pergolesi for a live demo of metrics and KPI visualization. So let me just unshare just 1 second. Can you confirm that you can see my browser?
Yes, we can.
Okay,
we can
thank
see
you
your
very
browser.
much. So this is the first dashboard. If you see here, I can select any of the scanner that are active. So for example, one of the possible demo is this one. They show on the left in function of the time. The time here starts from, sorry, I have my, okay, start from mid of August up to today. You see for this scanner the number of devices that was observed in this for each of this day when considering a time interval of 3 hours. So for example, this number 5,000 means that during a specific interval of time, scanners 4 observe this amount of different devices. What you have on the right is exactly the same information in which the heat map has the x-axis, again, the date, and the y-axis represent the time and of the day. And so from here, you can see very clear the weekly effects. And also you see that basically the people start to go around the area again around the beginning of September. And actually in October, I mean, at the end of September, actually we enter a kind of stable behavior. And if you observe, since we enter I would say, soft lockdown basically 2 weeks ago, you see the effect on basically this soft lockdown in Torino here. You see also that you can see also very easily the effect of the weekends on the hours, because the area is also was used by students for to have fun during the evening, and you can see clearly from here. Now, of course, you don't see. Here it is another scanner that you see have exactly the same kind of information. This other scanner 6 is one in the middle of a big crossing and with a lot of cars. And so if you see here, it is a very crowded place. If now I consider just one specific scanner, so let's say scanner 4, here I want to show you the results that we're referring starting from December 2019. And here it is up to March. So here clearly you see the effect of the Christmas holidays, and here it is clear. What is interesting here is that now we show the results with the number related just to students and Polytechnic employees. So the number that you have here, so these 1,000 over 3 hours, or these, I don't know, 400 over 3 years, are numbers on which we are sure that correspond to people, because they are not affected by randomization. Here you see clearly the similar habits in terms of weekend and weekdays that are common between students and employee, but at the same time you can observe that the habits in terms of going inside the campus area are different from professor and students. This is very clear. And of course you see the effect of the lockdown we start really during these days in Torino. If we now consider the most recent, more recent time window, for example, this refers to today, and this is starting from the beginning of September. So basically, you see the mid of August. I apologize. So basically, you see the last few weeks of holiday, and then you start to see the people come in the area of Politecnico, and you see also the effect of the lockdown. Here, exactly the same information, but just referring to students and employees. So the number that you observe here are numbers reliable. So this concludes the first set of results regarding the dashboard for the people density. Now let's consider the other dashboard. This dashboard allows to create in real time a drawing like this, in which we have the map. Automatically we have an arrow whose color represent basically the frequency of that path. And for example, you see here the list of all the possible pattern of mobility. In this case, by chance, there were the most likely, most observed path were just from pairs of Wi-Fi scanner. But if you see, sometimes there are also some pattern like 894, that is 8, 9, and 4. It is some pattern like this that were identified. Of course, I can change the date, the hour, and the time interval, and I can get the pattern on any given interval of time. So actually, this concludes the demo regarding the dashboard by which we analyze the the mobility pattern, mobility density in the area. And I leave the floor to Matteo to basically show the KPI metrics dashboard.
Yes, hi everybody, and thank you, Paolo. I'll try to share my screen now. Entire screen. Okay, I think you should now see my screen. Okay, so from up to now, we saw the dashboards for the specific data collected by the use case, but here we can see how the 5G portal integrates with the use cases by supporting them not only with the configuration, the deployment, and the execution of an experiment, but also in the collection of more metrics and more KPIs. So from the portal, after executing the experiment, in this case, the Smart City one, we can review the details of the execution of the experiment. So we have the site where the experiment was deployed, the ID, and more stuff, more details, of course. Then we can obtain some dashboards with more infrastructure-related metrics that are, for example, the CPU consumption, the number of active sensors registered by the use case, more CPU from different VNFs. In this case, we can monitor the storage, the memory consumption, and so on, while the use case is in the execution state. And apart from that, we can also compute and validate KPIs. So you can obtain from the portal this report that tells you if your KPIs were validated. In this case, for example, we defined one KPI on the CPU consumption to never reach the 95% or 100%, something like this. And the KPI evaluation was successful in this case. And more graphs are presented to you to show you what was the CPU value during the whole duration of the experiment and how it was going, how if something was unexpected, you can repeat your experiment with different settings, different values until your KPIs are satisfied. So this was a very brief presentation of what the 5G portal offers to the use cases. And yeah, that's all. I'm done. Thank you very much. And I leave the floor to Silvia, I think.
Thank you, Matteo. So your presentation complete our time slot dedicated to the use case Smart City. And now I would like to present the third presentation, the third use case. The presentation will be given by CNIT. Is the use case related to smart tourism. Claudio, I will leave you the floor.
Okay, thank you. Can you hear me?
Yes, we can. And now
okay.
You.
Okay. Also, the video should be fine. Sorry, there's a bit of a glare behind me, but I can't do anything about it. It's the sun. I'm going to share my screen. Let me know when you can see it.
We can see. Yeah. Yes. Now in presentation mode.
Okay. So. Okay. So. Now, this is the third use case that we're going to present to you today. As already briefly introduced by Silvia before, is about smart tourism. And this tries to intercept the need that visitors today have to improve and enhance their visiting experience using the digital capabilities of their smartphones and the support of the upcoming 5G network. This use case was completed, was worked on beside myself by three of my colleagues, Luisa Antionaivo, Luca Galleano, and Valerio Palma. The use case hinges around an application of augmented reality. Augmented reality, as you know, is a superposition of external features of what we perceive as the reality, superposition that happens on a digital frame, and that allows us to complement the experience we see by adding additional features. It can be used to enhance the accessibility and the information available in cultural sites, and it could be used to provide visitors to provide information on correlated things that they want to see, on additional historical information on the site that they're visiting, or the experience that they might be having if they chose, for example, to go and follow a specific path around a monument or a work of art or an installation that they are looking at. For this purpose, we have developed, first of all, a mobile app that runs on common smartphones that uses the built-in cam to show a view of the environment wherever the user points the cam, and superimposes on this view augmented reality features after identifying and classifying the work of art. So it's capable of recognizing the specific monument, a specific statue, or a specific building based on an existing database, and then superimposes according to the location and according to the monument we're visiting, augmented reality features such as menus or images or buttons, scroll down windows, and so on. Next, what we did is we integrated this mobile app with the 5G EVA Edge Cloud to allow the mobile app to download in real time and exploiting the blazing speeds of 5G, even heavy content such as multimedia videos or 3D maps. Here we see a very high-level view of the architecture of the use case. On the left, we have the smartphone running the mobile app that then interacts and associates to the 5G network and can access the 5G EVA Edge Cloud, where we have two virtual machines, the augmented reality server and the media database that are involved in this augmented experience for the visitor. For the purpose of this experimentation, we also have the augmented reality server connected with a visualization tool. I'm not showing here all the details that have already been shown by RS2T earlier on, so the interconnection with the Kafka bus and Filebeat, Elasticsearch, and Kibana, and so on, but they are also part of this architecture. Now, I am going to show you a live demo, live, so to speak, because as explained at the beginning by Mauro Boldi, at this time we're not allowed to be on the street to run a real live experimentation, but we did it in the previous days before the lockdown came into place. In the brief video I'm going to show you, you will see, first of all, the creation and the scheduling of the experiment, followed by its execution, which will consist in a view of the screen of the mobile device, showing through its camera an art installation in the Innovation Mile, where augmented reality features are superimposed, just to show you the capabilities of this app. And at the end of the video, we will see a brief presentation of the KPI measurements done during the demo. Okay, so let me try and now start the video. Okay, hope you can see it. We start by creating the descriptor of the experiment on the 5G portal. Then we schedule the experiment. After the 5G portal superuser has accepted the scheduling, we are ready to deploy and execute the experiment. Then we wait for the client to start the application. When the app is launched, it starts checking the user's GPS position and sending it to the server. The server performs a geographic query using the device position, and then it returns a list of media files related to the surroundings. Once the list has been received, the app starts downloading all the media files by sending another request to the server. Each button has its own function and it triggers a different content, like images, videos, information about events, links to websites, the 3D map of the site. And now we're going to see the dashboard showing the CPU load and the memory usage. The first two graphs are the CPU load for the database and the multimedia server, since we are using two virtual machines for these tasks. The CPU load is measured in percentage. The first peak area we see on both graphs, which is between 15% and 25%, relates to the request from the client and the response from the server. Then we have a graph for the memory of the multimedia server measured in megabytes. And we can see that it does not use much memory, reaching about 350 megabytes. Okay, this is all from my side. I'll give Silvia back the control.
Thank you, Claudio. Thank you so much. So we can now come back to the conclusion on our webinar. Share a couple of slides. Okay.
Silvia, unfortunately, we cannot hear you as far as I can see. Is
Okay,
there any?
was mute myself. Sorry
Oh,
for this. I apologize for that. So let me just share the last two slides about this webinar. So we would like to give some conclusion in order to summarize up what we have seen together. So we showed the two use cases strictly related to mobility in urban area, with the two complementary approach, as Paolo was well explained before. The macroscopic approach developed in Smart City to identify flow of people moving from one Wi-Fi scanner area to another one, versus a macroscopic mobility model provided by machine learning analysis of data series coming from sensors from mobile phone owned by directly end users involved in the use case execution. In an asset touristic experience, we have seen a smart tourism application requiring massive download and analysis and processing of multimedia content through the AR-based application that you have seen. And I think now it's clear if we compare 5G versus the 5G technologies, the comparison is straightforward. It says that we are comparing distributed data analysis approach versus a centralized one. So now the analytics, the data processing is enhanced and is distributed close to the data sources and allow large-scale applications. Facing with a high-density device that for the first time we can face in this way. So it's a very useful and straightforward way. And scalable applications are now possible and, of course, available for anyone. Of course, there are many applications. We just mentioned a couple of them during the execution of the three use cases, and they are all interesting for the vertical players, especially for the municipality of the city of Turin, who hosted this project and was partner in this project. I would like to conclude by thanking all people who made possible this webinar, not only the presentation, not only people that are on the stage with me now, so people from CNIT, Paolo, Claudio, Matteo, and from RS2T, but also all people from technical partners involved in the development and deployment of these use cases. So first of all, team that is not only the site manager, but also the leader of the Italian site partners. So I'm referring to Mauro Agus and his team, his colleagues who helped him also on the field. I would like to thank the technical team managing the Icon platform that were very useful in both in two of the three use cases, the Icon platform. I would like to thank Paolo Scarambro and his team for supporting us for all the tests we performed together. And of course, the technical and technological partners in the Italian site. So Ericsson Italia, and of course, Nextworks. So I would like to thank Giada Landi, Elian Kaja, Giacomo Bernini, and Gino Carazzo, who really helped us a lot, not only for the concept and the vision of the use cases, but also for the implementation and deployment in the web portal. And of course, all partners, all technological partners in 5G, that was amazing working with them. So I would really like to thank you, I think on behalf of all the people presenting with me this webinar, because people behind the curtains, really, they're really very amazing. So no more on that, but I think you can understand what I mean. So now it's time for a Q&A. I will give the floor to Mauro Boldi. If you would like to moderate this session, Mauro, go ahead.
Yes, thanks. I would like to thank Silvia, that was a perfect presenter of this webinar, and also the use case from RS2T, and Paolo and Claudio for their presentations. Of course, we have to apologize a little bit for the quality of some live presentation due to the fact that it was not live. As I explained at the beginning, we are in a lockdown phase here in Turin, and so it is not possible to run everything as we would have liked to do. I have also to tell you that these 3 use cases are actually 3 out of 4 that we are considering in 5G. 4 internal use cases. As you know, we are the platform that is used almost by all the other ICT 19 projects. So in the next months, until the end of the project, we will, of course, host a number of other activities in terms of use cases execution in our platform. Just some updates on these, because we are working on the multi-site activity. That is one of the very important features that have not yet been presented by us. Multi-site means that we will apply also our interworking layer, that is this orchestrator of orchestrators that is working in our labs here in Turin. Of course, in these use cases, you haven't seen it working because it is 3 use cases are actually 3 of them based in Turin. But we are developing in the project already some activities that will exploit the interworking layer completely. Quite an important achievement. On the other hand, as I said, we are also waiting for other use cases, not only in Italy, and for the use cases that will come from the other projects, also ensuring the sustainability of our platform after June 2021. That is actually currently the deadline, the ending time of 5G at the moment. So now it's time to answer some questions, if there are any from the audience. So I haven't seen actually any of them in the chat, so I don't know if shyness or if you actually would like to ask them now. So is there any question from the audience? It looks like that everything was pretty much clear. So I think that if we don't have further questions, just an announcement, because we are already preparing the next webinar, actually. That is the one that will be run jointly by 5G and 5G Tours project. It will take place in a couple of weeks. So there are all the announcements in our website and also through the usual communication channels in 5G PVP and 5G IA. In that webinar, we will show, of course, other use cases and that are also not only Italian, that are also jointly developed with 5G Tours. So it will be an important webinar before the end of the year. Okay, if there are no other questions, I once again thank Silvia, all the guys from RS2T, CNIT, Polytechnic in particular of Turin, Nextworks, Ericsson, Municipality of Turin, that are all working with Telecom Italia here in Turin to develop what you have seen today. Okay, thanks a lot for joining this webinar. Take care. See you soon in other webinars, and bye-bye for now.